So, I'm just playing some Minecraft, building a little something while listening to Jason Mraz talking about how there's too much food on my plate. When a remarkable, exceptional, amazing, astonishing, astounding, and marvelous question comes to mind. Ignoring anything that can make this physically impossible, how much force does Sonic need to exert to run at the speed of sound? And what are the physics behind all this? To start off, let's actually figure out what we need to solve in the first place. To do this, we'll need a little something called a free body diagram. This is just a diagram that shows us all the forces acting on something and the directions of those forces. When running, there are 4 different forces acting on Sonic: the gravitational force, the normal force, the drag force, and finally the force Sonic exerts on the ground while running. This is our main goal for this video, but first, we need to find all the other forces. Let's start with the simplest one, the force of gravity. When on Earth, Sonic, along with everything else on Earth, has the force of gravity accelerating him downwards at 9.8 meters per second squared. But he's not phasing through the ground. There must be another force pushing him upwards. This would be the normal force. Pardon my profanity, but what the heck is a normal force? Well, the normal force isn't just some made-up force that physicists use to make things easier. It's literally the ground's atoms pushing Sonic's atoms away, or in this case, upwards. Since Sonic isn't accelerating upwards or downwards, both the force of gravity along with the normal force have to cancel each other out to create a net force or total force of 0. This means that both forces must be equal in magnitude or strength, but opposite in direction, just like on the free body diagram. So once we find one force, we'll know both forces. The equation for the force of gravity is mass multiplied by the acceleration due to gravity. This is simple enough as we already know the acceleration of gravity to be 9.8 meters per second squared. This leaves us with Sonic's mass, which we can find quite easily thanks to Google. Yeah, sure. Thanks to Google, this is exactly what I'm looking for. Regardless, if we substitute the known variables into our equation, we get the force of gravity equals 35 kilograms multiplied by 9.8 meters per second squared. These two numbers multiplied together would give us 343 kilogram meters per second squared. Now, what does this mess of units even mean? Well, it would be a lot easier to know what it means once we simplify it. Newtons are the units that measure force, and conveniently, they're equivalent to kilograms meters per second squared. So we can replace all of this with newtons. This means that the force of gravity, and therefore the normal force, is equal to 343 newtons. Now, with both the normal force and the gravitational force taken care of, let's move on to everyone's favorite, the drag force, aka air resistance. Air resistance is the force that the air pushes back on something when it's moving through it. There are a couple different formulas for air resistance, but we'll be using this one. This is one mess of an equation, so let's go over every variable one at a time. Firstly, this fancy looking P is the density of the fluid, which in this case is air. Finding air density isn't very difficult, as we can just use this nifty air density calculator I found. At sea level and near room temperature at 70 degrees Fahrenheit, or about 21 degrees Celsius, air has a density of 1.2 kilograms per meter cubed. Now we have the dreaded drag coefficient to figure out. This one variable is why air resistance is such a headache for so many. The drag coefficient is how aerodynamic an object is, that is, how easily it can move through a fluid, especially at high speeds. This is mostly based on the size and shape of the object, but it's also influenced by the texture of the object, and probably a bunch of other factors too. For the sake of my sanity and the length of the video, we'll just be taking the size and shape of Sonic into consideration. Finding the drag coefficient is easiest for simple 3D shapes, like spheres and cylinders, for example. So what if we just model Sonic using only these simple shapes? Sure, it won't be perfectly accurate, but it's the only feasible solution I could come up with that would give a fairly close estimate without turning my brain into a nice, hot, steamy pile of mush. Conveniently, Sonic isn't a very sharp individual. That is, he doesn't have many sharp edges on the majority of his body, so for simplicity, we can imagine a model of Sonic consisting of only spheres and cylinders. Sure, his head has a bunch of spikes that could affect his air resistance, but let's take a look at this diagram I found on the Glenn Research Center website. When comparing the flat plane to the prism, the only difference is that the prism has a tail and the plane doesn't, yet the difference in the drag coefficient isn't all that significant. Especially since the back of a sphere sort of acts like a tail, considering Sonic's head as a cone with a rounded base wouldn't make much of a difference at all. For all the necessary measurements, we'll use modern Sonic from Sonic Generations as our reference. When running, Sonic tends to lean forwards and put his hands behind him, so we can ignore his arms, as the air resistance they create would be negligible, but we'll still be considering his hands. His head also covers most of his torso, so we'll consider his torso negligible as well. This leaves us with his head, hands, legs, and feet to find the drag coefficient for. Since Sonic is 3 feet 3 inches tall, or 0.99 meters, we can use this known measurement to find all the other measurements we need. For this handy dandy drag coefficient calculator I found online, all we need are some basic measurements for each of our shapes and the velocity, which we already know is the speed of sound. Substituting all our values and adding them together gives us Sonic's total drag coefficient, which is 1.619. Finally, with the drag coefficient out of the way, let's move on to our next variable, area. More specifically, this is the forward-facing area of an object moving through the air. This won't be nearly as complicated as the drag coefficient, as we already have most of the information needed. We can use the same shapes used to find the drag coefficient and just find the area of each shape's corresponding 2D shape. Spheres become circles and cylinders become rectangles. Once we add up all these areas, we get a total forward-facing area of about 0.2 meters squared. Finally, we have v, or velocity. Since Sonic runs at the speed of sound, the velocity would be 343 meters per second. That's it. It's that easy. Now, since we have all the variables needed, we can finally solve for air resistance. After substituting each variable for its corresponding value, we get 20,421, followed by this mess of units. This may look intimidating, but we can just combine all of these units and simplify it to get kilogram meters per second squared. If this looks familiar, that's because when we dealt with gravity, we got the same group of units, which are equivalent to newtons. This means that our final answer is 20,421 newtons. Finally, we can use everything we learned to find Sonic's applied force. But first, we need some background information. While running, Sonic pushes the ground backwards and downwards from his feet. But since he's pushing backwards, how does it create a forwards force? Well, Newton's third law states that for every action or force, there is an equal and opposite reaction. For example, if you punch a wall with 30 newtons of force, the wall will exert 30 newtons of force back onto your fist. For Sonic, he's pushing the ground backwards, creating a forwards reaction. But what makes this a lot spicier is that Sonic is pushing the ground at an angle. The easiest way to find this angled applied force is to find both the horizontal and vertical components of the applied force. Let's start with the horizontal applied force. Newton's second law states that force equals mass times acceleration. This means that the total acceleration is directly related to the total force. In this case, Sonic is constantly at the speed of sound while running, so he's not changing speed. This means that the total acceleration is 0. Mass is cancelled out due to the 0, giving us a total horizontal force of 0 newtons. Since this is 0, the sum of all the horizontal forces must also equal 0. We already know the drag force, and we're only missing the horizontal applied force, so let's call it x. But wait, why is the drag force a negative? This is because the drag force is pushing in the opposite direction of the applied force, so it has to be opposite in the equation too. From here, we can just use algebra to get x equals 20,421 newtons. This is Sonic's horizontal applied force. Now, knowing the horizontal applied force, we can try and find the vertical applied force. Let's do this using friction. When you hear the word friction, you may be thinking of something slowing down or making it harder to move. Or if you've studied physics, you may be thinking of all the trauma it may have caused you. But for running, high friction is crucial, which is why it's so hard to run on ice. This is exactly why when I read on the Sonic fandom that his shoes seem to have minimal friction to withstand the intensity of Sonic's running, I immediately knew something had to have been wrong. Minimal friction is extremely unideal for running, as it significantly increases the force needed to run. Since his shoes are made to help him run better, I'll instead be assuming that they have the highest friction possible. Alright, we get it. How do we actually solve for the frictional force? I'm glad you asked without me prompting you to, because the equation for friction is the coefficient of friction multiplied by the normal force. The coefficient of friction is a number from 0 to 1 that correlates to how rough a surface is. Since we're assuming the highest possible friction, the coefficient of friction will be 1. Alright, we know the coefficient of friction, and we found the normal force earlier, so we can find the frictional force so easily. Like many things in physics, it's not as easy as you may think. In order for the frictional force to be able to push Sonic forwards in response to his applied force, it needs to be strong enough to do this. Other than changing materials, the only way to increase friction is to increase the normal force. This would be done by the vertical applied force, since the reaction force created by the vertical applied force is an increased normal force. We don't want to have an extremely high normal force though, only what is necessary. Otherwise, our final applied force will be higher than it should be. So to find the minimum required normal force, we can have the frictional force equal the horizontal component. This makes sure that 100% of the friction's potential is being used without going overboard. We know that the equation for friction is the coefficient of friction multiplied by the normal force. But when considering the normal force from the vertical applied force on top of Sonic's original normal force, our equation changes into this. Once again, we can substitute all known variables and use algebra to get this value. And since the increased normal force is the reaction to the vertical applied force, we know that they must be equal in strength. Therefore, the vertical applied force is 20,078 newtons. Now, we have both the horizontal and vertical applied force, so the final step to finding Sonic's total applied force is to combine the two. This is actually really easy, as we can just substitute our known values into the Pythagorean theorem. Now, after all this time and hard work, we're finally at our answer. How much force does Sonic actually exert to run at the speed of sound? For Usain Bolt, this force is around 4,500 newtons. But for Sonic, this force is 28,638 newtons. Even after all of this, all the calculations, measurements, and hard work it took to get here, I still feel empty. You know what? No. Sure, this shows us that Sonic is strong and all, but it's not enough. We can push this further. According to Fiction Horizon, Sonic can instantly accelerate to the speed of sound. This article does have multiple grammar mistakes which can imply that it isn't a very credible source, but that doesn't matter. Acceleration is a measure of how velocity changes over time and can be calculated with this equation, which is the change of velocity over time. If Sonic accelerates instantly to the speed of sound from a standstill, this means that we can substitute time with 0 seconds, which corresponds to an infinite acceleration. Newton's second law states that force equals mass times acceleration, meaning that an infinite acceleration corresponds to an infinite force. Now, the way I see it, there are two options. Either Sonic runs at the speed of sound by exerting a massive 28,638 newtons of force, showing that he is not only the fastest but also the most powerful hedgehog on Earth. Or, Sonic runs at the speed of sound by exerting an infinite amount of force, proving that he is the strongest being in the known universe. The answer is up to you.